Hi, welcome back to the breadboard and another TI Tuesday. In the past we've been looking a lot at launch pads and booster packs that go on the launch pads. For the next couple of episodes I think we will have a look at some actual chips, and this week we're going to look at a high side current sensing chip. In this episode it's going to be the LMP8481 high side current sense chip that can actually work up to a positive rail of about 76 volts. Now, what makes current sense chips a little bit different from regular op amps is they have the additional circuitry to allow the inputs of an op amp to go to a very high common mode voltage. So even if your chip is working on, say, 4 or 5 volts, the inputs to the op amp can be as high as, in this case, 76 volts. But also with the chip we're looking at today, the actual supply voltage for the chip can also go as high as 75, 76 volts. But the output is still controlled by a voltage reference pin that is scaled between either 0 and Vref, or between effectively 0 and half of Vref, but it allows it, depending on the configuration, to be either bidirectional or unidirectional, so that it supports positive and negative current flow as well as positive current flow only. Now, the difference between this chip and some of the other ones, and hopefully in the next episode I'll have another sample chip arrived and I'll show you that one, is that this one first of all can go to a very high common mode voltage in that it's 76 volts, but secondly that the current sense resistor is not built into the chip. I have a few other ones that I will share with you in future episodes that have the current sense and everything else all built into it. Now, this chip is completely analog. There are no digital components to it, so it's not giving you out a digital reading via I2C or SPI or anything else to a microcontroller. So if you actually wanted to read the value, you would either have to use a meter or an A to D converter or something, or you could put a comparator on the output and have it detect an alarm state or something like that, which is actually something we're going to look at in a future chip that has that capability built in. Anyway, let's go to the breadboard, because the chips that I've got, I got them as samples from TI, and they're in SOT23 package. They're very, very small. So in order to put them on the breadboard, I have to be able to mount them onto a carrier first. So let's get that job out of the way, and then we will start setting up a circuit, and we'll have a look at a schematic on the computer, and then we'll give it a go. So these are the parts that we're going to need. This is the package of chips that came in. You can see compared to my finger how small the chips are. We're going to need some dip or inline pins. We're going to solder onto the carrier, and then this is the carrier that we're going to solder onto. Once we're done, we'll be able to plug this into my breadboard. Now, to do this, because it's surface mount, we're going to need to use either a very, very fine tip soldering iron, which we can do, or we can use a hot air gun. And what I'm going to be able to do today is my first official use of my new WXR3 soldering station that Weller sent to me a couple of weeks ago. That was a feature of a previous video that you can look on my YouTube channel. Now, because Weller provided me with a number of different tips for the WXP65 soldering pencil, I'm going to change the tip. Right now I've got one here that you can see that's quite large relative to the pads of the board that I'm using. So what I'm going to do is I have a much smaller tip. So I'm just going to quickly take the slide off and replace the tip with this 0.4 millimeter one that they provided. So we just slide it on the top, put the cover back on, and I'm also using 0.38 millimeter leaded solder. So I have an ESD mat that I'm working on so that I don't damage anything, and I'm just going to need to get a magnifying glass to see which way around that chip actually will go. So pin 1 right now is on the bottom right. I'm going to see if I can put a macro lens on the camera so you can see better. Now, this may not be easy because obviously with a macro lens it's going to get a little bit in the way of my soldering activity, so we'll see how we go here. This might be easier just to simply use a hot air gun, but I thought I would give this a try and see how well it works. Once I have one pad done, the rest of them should follow fairly easily if I can do this without moving anything. Okay, this side looks like it's ready to now solder. And I think there we have it. Just needed to add a little bit of flux just to make the solder flow a little easier. That's just something I'd forgot. Silly me. Anyway, it looks like we got some pretty good joints there. No shorts are visible. See if I can pick this up for a closer look. Yep, it's not perfectly aligned, but it's pretty good. All the connections are made. So that's good. So let's get the breadboard, the pins in. So this part's a little bit easier, seeing as these are all 0.1 inch pitch. I've just switched to my larger iron tip. Just solder these in. Just get one pin on each side first, just to make sure they're lined up, which looks good. Now we'll just get the rest of them done. So we just go away, give that a quick clean with some solvent, and we'll be ready to go to the breadboard. So for the sake of experimentation, right now I'm feeding the chip with 30 volts. That goes between pin 2 and pin 4, which is the supply lines. And I'm feeding via a precision digital voltage source that was provided to me by Ian Johnson of ianjohnson.com. He has a YouTube channel, does similar things to myself, and also builds a few products and shows people how to make them and sells them online. Anyway, he sent me a precision digital voltage source that I'm actually using to drive this here between this positive and negative probe, and I'm using that instead of a current sense resistor right now, just for this initial test. One thing that I discovered was that if I don't connect a resistor, I've got a 10K here right now, between one of the current sense pins and either the positive or the negative supply rail, then the differential voltage, just because it's not connected to anything, drifts out of range and the output goes to 0. So this is only here to just basically tether it down to a fixed known point so that the actual op amp will work properly. And now if I just zoom out a little bit, we will just have a look at the meters as well. Okay, that's got everything in view there. So you can see that I'm providing it with 50 millivolts right here, precision digital voltage source. The top multimeter, the Agilent 1272A, is reading the output on pin 5 of the current sense resistor. So because I've fed it with 30 volts, the output is actually able to go up to 12 volts maximum on its output. I just verified that in the data sheet. So in a lot of obviously microcontroller type of applications, you wouldn't be wanting to output 10 volts, but it does allow me to use this current source a bit better, because I cannot go below 50 millivolts on the output of this. If I actually try to go 0.01, it will not let me. Right, its minimum is 50 millivolts. Now Ian has a new version of this which actually will let you go all the way down to 0. The one I have doesn't do that at the moment, so 50 millivolts is the minimum, and with a gain of 100, you can see up here we have an output of 4.987, and you can actually, normally you would have this actually connected. You can even short it to the positive rail depending on the application node and what you're trying to measure. Now in a positive high side current sensing, it would normally be connected to the high voltage rail anyway, which is what the design of this is, and we'll try and reconfigure this in a minute to actually power the whole chip with, say, 5 volts if you were using it to a microcontroller, and then have the input even running up as high as 30, 40, 50 volts. We'll see what we can set up on the power supply, and we'll just verify that configuration. Anyway, for now, I can go up to 12 volts on the output. So if I change this from 50 millivolts to 100 millivolts. You can see with 100 millivolts going in, I've got 9.978 volts. Now my adjuvants are not, they're not 0.00 anything percent accurate. They are very accurate. They're 4.5 digit. But you can see here that that's pretty close to the gain of 100. And I'm not using a precision sense resistor or anything like that. I've just tied the VREF inputs to ground right now versus splitting them between the two rails. So I can go up a little bit more. I can put in 0.12 and that will take the output to the 12 volts, as you can see there. If I try and go up to say 0.2, so 200 millivolts, that would actually try and get an output of 20 volts, which of course it can't do, even though the supply is sitting at 30 volts, because the output is limited to 12 volts maximum. So if I go now back down to, let's just say 50 millivolts again, so that the output is at 5 volts, and I will reconfigure this now so that we have a 5 volt supply on the chip, and we'll have the current sense input floating on using a common ground, but we'll have it floating on say 30 volts or something, so that is way higher, and we'll re-verify that this is still working correctly and demonstrate that the common mode output works very well. Either that or we'll smoke the chip. So what I now have is the supply voltage of the chip is actually being supplied by 5 volts from my power supply, and if I just take the output meter for a second and just hook it onto the supply pin, which is the yellow wire here, which is pin 2, you'll see on the meter it's reading 5 volts. And if I put this meter also on the high side of the current sense input, which would normally be the current sense resistor, which is here, you'll see it is sitting at 30 volts. So I actually have the chip input, the common mode input voltage, way above the supply of the op amp. Now if you normally do this with a regular op amp, you'd probably smoke it. In this case, it's not warm or anything like that. I didn't expect it to be, and it's performing very well. I've got input of 50 millivolts still, and my output is still sitting nicely at 5 volts. So if you were using a A to D converter on an Arduino or something like that, it would be working just fine. Now of course, if you're using a current shunt resistor, here's an example right here. I'm not going to connect it right now because I don't have something that can drive enough current to do this, but what you would have is your current going through the outer 2 pins, and you'd measure your inner 2 with the 5 volt rail. So when you have the high side current sensing for say a power supply or a solar charger or something like that, and your inputs are very high, and it's often, you'll commonly find 30, 40, 50 volts on the output of even a lab bench power supply, or with a solar array you could easily have 40, 50, 60 volts coming out of the solar panels. If you're trying to measure that current, you either have to have a separate floating supply for your control circuitry like this and your microcontroller and everything else that's sitting on that supply to be able to measure it, or you need to be able to have something that can have a very high common mode voltage that can exceed the supplies of the actual measuring device and bring those sensed voltages down to within a range that your A to D converters and your microcontroller can handle. And that's where things like this chip comes in, where it allows you to run it on a logic level. In this case, it only goes down to 4.5 volts. So really more aimed towards a 5 volt one. But then you can, using the VREF pins, set it so that the output will only go to say 2.5 volts. So what we're doing right now is we're demonstrating that we can have a supply from say batteries or a solar panel or something like that, and in this case I've got 30 volts coming in here. There's the positive sense, negative sense, and I've got deliberately just superimposing using this precision voltage source a 50 millivolt current sense, which would represent an amp going through this current sense resistor, which then results in 5 volts on the output. Now obviously if you've got different load characteristics, you can pick a chip that has a lower gain. You can get a gain of 20 or 60 or 100, or you can pick a smaller current sense resistor that would result in a lower output voltage as well. Now once you've got that, you can be running your chip, say on 5-volt rail, by reconfiguring the reference inputs, and we'll do that in a moment, you can actually get either a bidirectional current swing, which we can simulate by just switching these probes, or you can have the input to the ADC sitting slightly above zero, because one thing with most op amps and things, their outputs can't go to exactly zero. So yeah, most op amps will not go completely to 0 volts. Now you can do a few little tweaks with this that will allow you to do that, playing around with the voltage reference, and it's detailed in the data sheets. We'll have a look at that in a moment. But what you can also do, which would allow you to have current measurements in both directions, is to center the output to about 50% just by tying one VREF to high and the other VREF input to 0, which would effectively split the volts coming out to 50% for 0 current flowing through the sense resistor. I had a jumper in here between 6 and 7, which was effectively connecting ref A and B together, and then I've got this green wire that was connecting it to ground, and that basically made the output swing from 0 to the supply voltage up to a maximum output of about 12 volts. What I've done now is I've taken reference A and I've connected it to the positive supply, which is going to be 5 volts. Reference B is still going to ground. So if you remember the input circuitry, I'll just put it up now on the screen so you can see it. You'll see there that we're effectively dividing now the supply rail in half, or effectively supplying it with a 2.5 volt VREF. As you can see now, I've got the VREF A to the positive supply, which is 5 volts. VREF B is still going to ground, which means that the reference input to the last stage op amp is going to be the 2.5 volts. Now, I've shorted the current sense so that it appears that there is no current flowing, and you can see now that the output is 2.495 volts, so basically 2.5 volts, which is exactly half the supply rail. So now if I input the 50 millivolts, it's going to go up, but it's only still going to go up to the 5 volts on the output. So it's still a gain of 100, but it's been offset. So if I now change this to be the correct output. So now I got the input shorted out on the current sense. I've introduced another multimeter here to show what is actually currently across the input, and I've got a 100 ohm resistor there as well. So if I feed the input directly with the 50 millivolts, you'll see that my output is now going up to there, but of course that's not going to work very well because it's got a gain of 100. So 2.5 volts plus the gain of 100 is going to take it on 50 millivolts is going to take it to 7.5 volts. And my supply is only 5 volts, so that's not going to work at all. So I need to be able to reduce this voltage going in. So what I've done is I've got a 100 ohm resistor and a 1K resistor across the sense input here. So I've got this 1K, which I'm going to feed the 5 volts into, and then across the current sense input I've got 100 ohms. So it's 1K and 100 ohms, so basically I'm going to get a tenth. So my 50 millivolts should only give me 5 millivolts, which should give me about a half a volt offset from 2.5. So if I feed in 50 millivolts, I should get about 3 volts on the output. So that's what I'm hoping, if I've done my math right. So let me just change this to the other side of the 100 of the 1K. Now, I don't know how accurate. Obviously, this 1K and 100 ohm are not very accurate. They're only 5% resistors. Plus, it's a 1K and a 100 ohm, not a 900 and a 1K and a 100. So it's not an exact. It's more of an 11 to 1. So we actually have about 0.4 volts coming out. So if you add 0.4 onto 2.5, you will get about 2.9, and that's almost exactly what we have on this other multimeter here. So now what I can do is, if I increase this now to say 100 millivolts in, so 10 millivolts going in, because you've got to divide by roughly 10. All right, so we've got 3.3. Now if I just tweak this so that this 84 is closer to 100, that means we should have about 3.5 on the out. So now what I've got is, it's a little bit high there, but you can see that I've got 100 millivolts going in, 10 millivolts going in, and I've got about 1 volt offset from the 2.5 that was going out. So it's still now working with the volts that I had, but the difference now is that if I go below on the input, if I go below the 0, so I go to negative, or I reverse the current flow, now I should be able to take this back to lower than 2.5. So if I actually short this out, you'll see I'm back to the roughly 2.5. Now obviously because of the resistors and everything else, it's not really doing what I expect it to. If I just take this and actually short it out here, you'll see it's 2.5. Because of all the resistances and the internal feedbacks, it's messing it around a little bit. So you can see there's a little bit of an offset on this one. So now if I reverse this with 50 millivolts, it's going to take a half a volt away from the 2.5 volts. And as you can see now, that is exactly what it's doing. I put 50 millivolts in, divided by roughly 10. So I've got 5 millivolts going in here, and I've taken off the 500 millivolts on the output. So now if I make that 150 millivolts, or 100, let's just do for now, then we'll take another half a volt off of that. And if I make it 200, which is effectively 20 millivolts here, less a little bit, then there should only be half a volt left, which there is. If I try and increase this, I don't know how quick, it's a bit crude from the, oh, just happened to get it exactly right. So I've got pretty much 20 millivolts going in the negative direction, and my output is now showing 50 millivolts, which is really good. So if you were using a battery charging circuit as an example, you would use your 50% bias, or use a 2.5 volt voltage reference. Or if you're using an ADC that's only, say, going from 0 to 2.5 volts, then you could use a 1.25 volt voltage reference. And you can drive the input now either plus amps, or for charging, and maybe negative amps for discharging. So this would now be able to measure quite easily bidirectional current flow, and you would just feed it into the ADC, and you would just set your calculations so that it was reading 0 current for say it was a 1024 count, so a 10-bit ADC. Then if it was reading 512, you would basically say that was 0 volts. 0 current, and then anything up to 1023 above 512 would be positive flow, and anything towards a 0 count would be negative flow. So that's basically this chip in a nutshell. We'll go back to the data sheet for a second, and then I'll wrap this up. I didn't want to make it a long video, just informative on this high side precision current shunt. Now, you wonder why you might use this instead of a straightforward op-amp. As I've already said, this has the built-in capability of far exceeding its common mode input. As I said, right now I'm driving this with 30 volts on its input, and on the current input, so it's elevated on 30 volts, but the supply for this is still sitting at 5 volts, so it's perfectly compatible with TTL logic or something like that. And if you then wanted to feed this into a 3.3 volt ADC, you would just adjust your VREF out so that it wouldn't exceed the input tolerances of the ADC, or you'd put a voltage divider on the output of this to bring it down into the range that you wanted. Either way though, chips like this current sense resistor from Texas Instruments allows you to easily implement a current sensing solution without getting into complicated supplies or higher parts counts. As you can see here, the only thing outside of the chip that I've actually had to add here is a divider resistor, and that's only because I didn't have the ability to put a small enough voltage right now into this to simulate a lower current or a negative current. What I will do for the next episode is I will set myself up with a DC load and maybe a battery or something like that, so that I can actually control a decent amount of current through a shunt resistor and have it driving through in here so that we can actually see things working a little bit better. Anyway, that's it for now. This is another TI Tuesday, and we will see you next week.